Let's practice solving some GCF application word problems together. In number 1, Mr. Lee has 48 pencils and 36 erasers. If he wants to give out all the pencils and erasers to some students so that each of the students get the exact same amount without any extras, what's the greatest amount of students Mr. Lee can give the pencils and erasers to? Also, how many pencils and erasers does each student receive? So this right here is a classic GCF word problem because we're giving out all of the pencils and erasers, and also we're trying to figure out the greatest amount of students that we can give them to. So we're going to go ahead and solve this GCF problem, but I'm going to go ahead and use the ladder or the cake method just because it's a little quicker, okay? Feel free to use the prime factorization method if you would like to, but over here we can see that 48 and 36, what is a common factor? Now, I can think of some bigger numbers, but what I'm going to do is I'm going to use some smaller ones that you may think of as well. If you use bigger numbers, that's also perfectly okay if you have a smaller cake than me. So 2 goes into 48 24 times, and 2 goes into 36, let's see, 18 times. And I chose that just because they're both even numbers, so that's usually a nice easy one to start with. Then for 24 and 18, you could use 2 again, but I do notice here that they have 6 in common, also 3 and 2, but I'm gonna go ahead and just use 6 at this point. 6 times 4 is 24, and then 6 times 3 is equal to 18. And I think 4 and 3 are now relatively prime. Their GCF is 1, so we can stop over there. And that means this 2 times 6 on the side here is gonna tell us what our GCF or greatest common factor is. So this 2 times 6 is going to equal 12, so the GCF is equal to 12. Now, what does that actually represent? Well, the GCF equaling 12 means that we could divide all the pencils and erasers evenly, and that's the greatest number of students. So we can say that this would be 12 students would be the most amount of students that we could give these pencils and erasers to. So I'm just going to go ahead and box that first part, because that's one of the questions that was asked. And then next part is we're going to go ahead and see how many pencils and erasers. So it says how many pencils and erasers does each of these students receive. Now that's where we use these numbers here of 4 and 3, right? Now there were more pencils than erasers, so this 4 represents that each student is going to receive 4 pencils, and the 3 represents that each student is going to receive 3 erasers. Alright, so each student's going to receive a total of 7 items, and there would be none left over if we gave 12 students 4 pencils and 3 erasers each. Here's number 2. For number 2, we see that Benny has 42 burritos, it's a lot of burritos, and 56 tacos, that's even more. If he wants to give out all, so again it's all of the burritos and tacos to some students so that each student gets the same amount, that's a key word here, so you gotta be fair to everyone without any extras. What's the greatest? That word kind of pops up again here, so we know it's a GCF problem. What is the greatest amount of students that Mr. Lee can give the burritos and tacos to? So Benny and I, or Benny and Mr. Lee, are going to be giving out these burritos and tacos to. Also, how many burritos and tacos does each student receive? All right, so we're going to be giving out lots of food here. Just like in the last example, I'm going to go ahead and use that ladder method. So I'm going to put 42 and 56 right next to each other here. And let's see what goes into both of these. Now, I'm thinking about some different times tables, maybe 7, right? 7 times 6 is 42, and 7 times 8 is 56. So 7 times 6 is 42, and 7 times 8 is 56. Now, 6 and 8 are both even numbers, so they can't be relatively prime. So they must have a GCF of 2 if they're even. 2 times 3 is equal to 6, and 2 times 4 is equal to 3. And remember, 3 and 4 are relatively prime. And then our 7 and 2, or 7 multiplied by 2 on the side here, are going to tell us our GCF. So we're going to go say 7 times 2, so our GCF here will be 14. Now what does that actually mean? That means that we have 14 different students that we can give, Benny and I can give these burritos and tacos to. That's the most amount of students we can give food to so that everyone can get the same amount with none left over, okay? Now if we're gonna go ahead and see, well, how much will each of these students get? How many burritos? Well, there were 42 burritos split between 14 students. That's gonna be 3 burritos each. All right, go ahead and write that. And then what does the 4 represent down here? The 4 represents if there were 56 tacos and they were given to 14 students or split evenly, each of those 14 students are gonna receive 4 tacos each. All right, so total of 14 students. The number of students here represents the GCF, and we can give 3 and 4 burritos and tacos to each of these students. Here's number 3. For number 3, we see that we have rectangle A, rectangle A has an area of 56 square meters, and then we have rectangle B. So we have two rectangles, and this has an area of 42 square meters. Assuming that all dimensions of the rectangles are whole numbers, meaning no fractions or decimals, it says what's the greatest matching length. So greatest, that kind of tells us we're doing GCF. And then it says matching length, so there has to be something in common, so greatest common, can these rectangles have? What would their widths be? Okay, so let's go ahead and imagine what these rectangles are looking like. Now rectangle A could be a whole bunch of different things, right? Rectangle A could have tons of different dimensions, but we're looking for the dimensions where they are matching. So let's just go ahead and see if we can lay out all the different possibilities that rectangle A could look like. Okay, so we know the area is 56, but if it has whole number dimensions, that means it could be like 1 by 56, right? 1 for the length and 56 for the width. It could also be something like 2 times 28. It could also be something like 4 times 14. Also maybe something like 7 times 8. And then it could be all of the reverse of these as well. It could be 56 by 1, 28 by 2, 14 by 4, and 8 by 7. So you could write out a prime factorization and then get this full factor list as well. But I'm just going ahead and showing you that these could be the dimensions of rectangle A, assuming that there's no fractions or decimals. And then let's take a look at rectangle B. So for rectangle B, and if you were already kind of imagining this, that's good, but I'm just trying to lay it out so it's a little bit more clear. Rectangle B has an area of 42, so it could be 1 by 42. It could also be 2 by 21. It could also be maybe 3 by 14. And it could also be maybe 4 by, nope, not 4 by anything, 5, 6 by 7. Okay, so these numbers are actually pretty familiar maybe from number 2 if you notice that. So we could notice that we could have some matching lengths here, right? So we could put these rectangles side by side and they could have a matching length of 1, or they could have a matching length of 2, or they could have a matching length of 7, or they could have a matching length of 14. So it looks like these are all possibilities that you could line up these rectangles. So if you like these lists of factors that can be more clear, it says what's the greatest matching length? So if we drew this rectangle A on the side here and that was 4 by 14, maybe it would look something like this. I'll label it as rectangle A. And then for rectangle B it would be 3 by 14. So if we would go ahead and label that one, maybe rectangle B would be next to it, but 14 would be the common length here, right? So this length in the middle would be in common. This would be 14. Go ahead and label it as 14. And then the 3 would be maybe the width here, and then 4 would be the other width, right? So rectangle A has a bigger area than rectangle B, just because we knew that from the beginning. And so they would share this dimension of 14. So in terms of the question asking about what would their greatest matching length be, it turns out that's their GCF, right? Their greatest matching length that they could have here would be equal to 14 meters. I'm just go ahead and label that just like this. 14 meters would be the greatest matching length. And if they had a matching length of 14, the question does ask later on what would their widths be, right? So this 4 that's left over, the one width for rectangle A would have a width that's equal to 4 meters. And then for rectangle B, that one would have a width of this 3 meters. So that's equal to 3 meters. Okay, so these two rectangles would have a matching length of 14, and then their individual widths would be 4 and 3, so that their areas would be 56 and 42, which is what we started with, right? Now, if you wanted to use the ladder method, you totally could. You could just take this 56 and 42 and put them next to each other, and then just go ahead and find some common factors, like maybe 7. 7 times 8 is 56, and then 7 times 6 is 42. And we kind of went over this in number 2, so I'm not going to spend too much time on this one. 2 times 4 is 8, and 2 times 3 is 6. And then you can see here that we're done because 4 and 3 can't go any smaller. Their GCF is 1, and so 2 times 7 does get you this 14 that we ended up getting anyway. For number 4, this one's pretty similar to number 3, so we could try to apply that same strategy. We have rectangle C here, has an area of 80 square feet, and then we have rectangle D, and that has an area of 96 square feet. So assuming all dimensions of the rectangle are whole numbers, so no fractions or decimal, it does say what's the greatest matching or greatest common length that these rectangles can have, and then what would their widths be. All right, cool. So pretty much the same problem, just with different numbers. So on number 3, I listed out all the factors. I'm actually just going to go straight into the ladder method just because it's a little quicker. Hopefully that did give you a good visual earlier. So if you want to know what the other possible dimensions were, you could see them listed. That's what's useful about writing all of them out here. So rectangle C is this one on the left. So I'm just going to C up here just to label them. Let's put rectangle D up top as well, so we know which one is which. Now 80 and 96, they're pretty big numbers, so maybe we can start with 2 because they're both even. Now 2 times 40 is 80, and then half of 90 is 45, and half of 6 is 3. So 45 plus 3 is 48. Okay, we can go ahead and they're both even, so we definitely can go again here. You could use 2, but I'm noticing that maybe we could use 8, just because 8 times 5 would be 40, and then 8 times 6 would be 48. And at this point, 5 and 6 have nothing in common, and we can notice here that the 2 and the 8 on the side would get us our GCF if we multiply those common factors together. So let's see, 2 times 8 is going to be 16, so we know the GCF is equal to 16. All right, so based on that, we know what the common length would be. So this first rectangle, rectangle C, would be 5 by 16. So maybe we can go ahead and write 5 by 16, make like a rectangle. It's not really drawn to scale, but that's okay. So like 5 would be over here, and then 16 would be over here. This would be rectangle C, right? And this would be that 16 that it's sharing, but that's going to be shared with rectangle D. Now rectangle D has a width that's a little longer. It's 6. We're doing 6 by 16, right? So it's a little bit longer. I guess they kind of look similar, but I'm going to label this one 6, so it's a little bit longer. So if you were to find the area of C, 5 by 16, that would be 80. If you multiply them, and then 6 by 16, that would be 96. So to put these rectangles have matching lengths of 16. So in terms of their greatest matching length that they could share, I'm going to go put that here, the matching length. We found out that's going to be 16 feet. Okay, so that's going to be answering that first part, and whatever their greatest matching number is, that's their GCF. So that's the application of the whole concept of GCF here. And then what would their individual widths be? For rectangle C, the width would be 5 here. So we can say that the width is equal to 5 feet. And that makes sense because 16 times 5 is 80. And then for rectangle D, the width that we're going to put for that one is going to be 6 feet. So let's go ahead and put 6 feet for D, and 6 times 16 does get us 96. So that also makes sense here. Alrighty. So there are the matching lengths, which is 16, that's the greatest one, and then the width are going to be 5 and 6, respectively, for C and D. Let's look at number 5 now. At number 5, we're at Chipotle, and the kitchen staff made 96 burritos. Then they made 144 tacos, and then 224 quesadillas. The staff had to prepare platters for a catered lunch in Mr. Lee's classroom. Thank goodness, I love Chipotle. Each platter will have the same number of burritos, tacos, and quesadillas. How many platters can the staff make if they want the greatest number? Okay, that greatest number kind of comes out again. Number of Chipotle items on each platter. So right away, I'll put this 96 and 144 and this 224, so all three numbers next to each other. And let's see, I'm gonna go ahead and label them as well. So right from the beginning at the top here, this is talking about the burritos, 96 of those. And then for the 144, that's the tacos, and then put a T. And then for the quesadillas, there's 224, I'm gonna put a Q. All right, so we know which ones we're talking about. Now these numbers are pretty big, but notice how they're all even. So you can go ahead and divide them all by 2. So I'm gonna start with that. And so 96 divided by 2, I think we did that in a previous problem, but that's 48. Half of 144 is gonna be 72, and half of 224 is gonna be 112. All right, now can we go again? I think so, right? These are all even numbers, so we can definitely divide all by 2. All right, so I'll just do that because it's a little bit easier. Half of 48 is 24, half of 72 is 36, and half of 112 is 56. All right, they're all even, so we can definitely go again. I'm gonna see if I can find a bigger number this time. Maybe I do see one, but I'm going to go with 2 because that's probably what most people are going to notice. 2 times 12 is 24, 2 times 18 is 36, and 2 times 28 is 56. But notice how they're all even again, so we could have done 4. I just think that maybe not as many people know 4 times 14 is 56. So I'll put a 2 here. 2 times 6 is 12, 2 times 9 is 18, and 2 times 14 is 28. So I think at this point, 6, 9, and 14 are relatively prime. There's no other number besides 1 that goes into all of them. And then so we can go ahead and multiply all the 2's on the side here. So 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So that means the GCF here would be 16. But what does that actually represent? That means that we could make 16 platters, right? We can make 16 different platters that have the identical number of burritos and tacos and quesadillas. That's the most amount of platters we could make. And while the question doesn't ask how many of each type of food will be on there, if you did want to know, there would be 6 burritos on each of these platters, there would be 9 tacos on each of these platters, and there would be 14 quesadillas on each of these platters. Here's number 6. For number 6, Jeremy has 2 pieces of wood. One is going to be 90 inches long and the other one is going to be 72 inches long. He wants to cut both pieces of wood into some smaller pieces so that each of all of these pieces are going to be the same length. So that's a key word. So things are going to have to be in common. He wants the pieces to be as long as possible, so the greatest, and doesn't want to have any lumber left over. So everything has to go in evenly. How long should each piece be, and how many total pieces of lumber will he have? So kind of a different question here, right? Now we have the 90-inch piece of wood here, and then we have the other one that is 72 inches. So let's just go ahead and put them side by side. I'm going to use this ladder method right from the beginning, and let's see here. The first number I think of, you could use 2, but the one I think of is 9, just because 9 times 10 is equal to 90, and then 9 times 8 is equal to 72. So you have 10 and 8, but they're both even numbers, so we can definitely divide them both by 2. So we put a 2 here, 2 times 5 is 10, and then 2 times 4 is 8. And I think this 5 and 4 are now relatively prime, they have nothing in common. So 9 and 2 on the side here, 9 times 2, that's going to be 18. So the GCF here is going to equal 18. But what does that mean for this problem? So what does this GCF of 18 actually mean in the context of this problem? Well, remember this 90-inch piece of wood. Let's go ahead and label this 90-inch piece of wood. And we're basically cutting it up, right? We cut it up and we knew 18 went into it evenly. So we have these 5 pieces, and they're each going to be 18 inches long, each 18 inches, right? Now, while that takes care of the 90-inch piece of wood, let's look at the 72-inch one. So that one is shorter, so it's 72 inches. So we found out that we could break that up into some smaller pieces as well. And this one is going to be 4 pieces, all right? And 4 pieces, and each one of them are going to be 18 inches long. Right? So if you're wondering where those numbers are coming from, for the one we did the 90, we knew that we could do 5 pieces of 18 each. And then for the shorter one that's 72 inches, we could do 4 pieces that are each 18 inches long. Now remember, there were 2 main questions that we were asked. The first one was, how long should each piece be? And so to answer that question, we can go ahead and say that each piece should be 18 inches. Right? That would be the longest they could possibly be while all being the same length. And then for the second question that it does ask us, how many total pieces of lumber will he have? So we knew from the 90-inch piece of wood that we could cut 5 that were each 18 inches long. And then from the 72-inch piece of wood, we could cut 4 of those that were each 18 inches long. So 5 plus 4, that must mean that there would be 9 total pieces that are each the same length here. So that would be that second answer to that second question. Here's number 7. For number 7, we can see that Haley has 18 oranges, 27 pears, and 12 bananas. All right, it's a lot of fruit. She wants to make fruit baskets with the same number, so it means common, same number of each fruit in each basket. What's the greatest? So I think we're talking about GCF, some keywords in the word problem. The greatest number of fruit baskets that she can make. So that's the first question. The second question is how many of each type of fruit, so how many of each type of fruit will be in the baskets. Okay, so let's see here. We have 3 different numbers again, so this is not too bad. It's just like number 5 in terms of having 3 numbers. So we have 18, 27, and 12. We can just put them next to each other and use this ladder method or cake method. So I'm gonna just put O for oranges on top here, put P for pears, and then B for bananas. All right, so what do they all have in common? It looks like maybe 3, right? 3 times 6 would be 18, 3 times 9 would be 27, and 3 times 4 would be 12. And looking at the 6, 9, and 12, I don't think they have a common factor besides 1. 6 has 2 and 3, and 9 has 3 and 3, so they both have 3s, but 4 doesn't. 4 breaks into 2 and 2, so that one has something in common with the 6, but not the 9. So we can't go anymore. This 3 on the side just tells us right away that our GCF, the GCF here is going to be equal to 3. And what does it actually mean? Well, that's the greatest number of baskets. So we can say that 3 would be 3 baskets. It's the greatest number, our greatest factor that goes into all 3 of these. So we can only make 3 baskets. And that would be the most amount. And how many of each fruit would go in? Well, we notice here that if we had 3 baskets, 18 oranges split into 3 baskets, that would be 6 oranges in each basket. We also can see that if we split the 27 pears into the 3 baskets, there would be 9 pears in each of them. And then finally, for the 12 bananas split into 3 baskets, there would be 4 bananas in each basket as well. So there would be a total of 19 pieces of fruit in each basket, consisting of 6 oranges, 9 pears, and 4 bananas each. And let's take a look at just one more for number 8. We can see here that Madison is making activity baskets to donate to a charity. She's so nice. She has 12 coloring books. She has 28 markers and 36 crayons. What's the greatest number? So it's like greatest common factor. Greatest number of baskets she can make if each type of toy is equally distributed among the baskets. That's the first question. The second question, so greatest, we're looking for the GCF. Second question is how many of each supply will go into each of the baskets. So just like the fruit in the last problem, just some different numbers here. So let's go ahead and just write these numbers next to each other. So we have 12, and then we have 28, and then we have 36. Okay, so just putting these all next to each other, and let's see. The 12 is dealing with the coloring books. I'll use B for books, just because we have 2 things that start with C. Let's use M for the markers, and then C for the crayons, okay? Now we're looking to split these up evenly, all of them, so I'm thinking maybe 4 goes into all of these. 4 times 3 is 12, 4 times 7 is 28, and 4 times 9 is 36. And I think we have to stop here because 3 is prime, 7 is prime, 9 has 3 times 3, so it has something in common with the 3, but not with the 7. So that must mean that 4 in this problem would be the greatest common factor, or the GCF. All right, so well, the first question is what's the greatest number of baskets? That answer is going to be 4 baskets. That's the most amount of baskets that they can make. They could make 2 baskets as well if they split everything in half, and they could just make 1 big basket and put everything in there, but that's not the greatest number of baskets. Okay, so 4 is going to be that. Now, how much of each toy or item is going to go in each one? So for the, what is this? The B is for the coloring books, so that's going to be 3 coloring books. Are going to go in each of these 4 baskets, and then let's see, the 28 markers are going to be split into the 4 baskets, so it's going to be 7 markers each. And then finally we can see here that the 36 crayons split into 4 baskets. That means there's going to be 9 of these crayons in each of the baskets. All right, so we can see here that these would be all the toys or the items that are going to go into each of these baskets. There will be 19 different things in each of these 4 baskets. 3 coloring books, 7 markers, 9 crayons, and none would be left over. So there you have 8 different practice problems on finding the GCF. Specifically, these were application word problems, so applying the concept of GCF in some different scenarios where you might find them useful. So if you found this video helpful, please consider giving it a thumbs up. And as always, keep up the great work, and I'll see you in the next one.